and that's a huge number. This technology has potential to significantly reduce those numbers as it's commercialized and be applied in different fields. Specifically on the clothes dryers, mainly because our project was focused on the clothes drying applications, but the IP that we developed can be applied on different drying technologies. Let's focus on the clothes drying in the residential buildings. Almost 85% of American homes have clothes dryers, and that accounts for 6% of the utility bills in residential buildings, and that's a large number. It's somewhere about $9 billion energy bills goes just to the laundry or just to the clothes dryers, and that's a huge number. It's expected that the average sale of clothes dryers in the United States keep growing with a rate of 1.8% in the next few years. Conventional clothes dryers work based on the evaporation of water or based on heating. What they do is that they take electricity from the wall outlet. They have a resistive heating element. As air passes across that resistive heating element, it heats up, and the hot air passes across wet fabric and evaporates water, and that's how they achieve drying. But the latent heat of evaporation of water is so huge. It's somewhere about 2,400 kilojoules per kilogram of water removal. So the process overall is very inefficient. And considering all the inefficiencies in the conventional dryers, actually they are operating at their at 55 to 66% of their theoretical efficiency limit. So there is not much room for improvement in the existing improvement of the efficiency in the existing dryers. Conventional dryers have energy factors of about 3.5 pounds of dry blown fabric per kilowatt hour of energy you're putting, and they have drying time of about 40 to 60 minutes. Some newer technologies that are based on the heat pump, heat pump dry technologies, they achieve a slightly higher energy factor of about 5.5, but the drying time is slightly longer. It's about 60 to 120 minutes. So what we developed here, or what we proposed, was that conventional dryer use heat to evaporate water, and latent heat of evaporation of water is so huge. So instead of doing that, we proposed to use high-frequency vibration to shake fabric at high frequency, and when you are shaking fabric at such a high frequency, actually moisture comes out of the fabric in the form of cold mist. So we are not evaporating water, we are just mechanically extracting the moisture from the fabric. How we achieve high-frequency vibration is using piezoelectric transducers, also some people call them ultrasonic transducers, and that's how we generate high-frequency vibration. Let's go a little bit dive into the details. Let's say we have oscillating systems that have oscillation like A sine omega E, where omega is the frequency of the oscillation. The driving force that tries to take the moisture out of the fabric is proportional to the mass of the droplets inside of the pores of the fabric times acceleration that is induced by piezoelectric transducers. What is resisting against moisture removal is actually capillary force that's proportional to the surface tension times the diameter of the pores. If we want to show it in a graphical form, if we do the analysis, some basic analysis, as you can see in the figure on the right, for different pore sizes, the x-axis is average pore size in the fabric in micrometer, and the y-axis is final remaining moisture content in the fabric. So at low frequency, like the green line, for very small pores, actually we cannot remove the moisture from the fabric, mainly because the surface tension or the capillary force is large, and we cannot remove the water from the fabric. But if the pore size become larger, definitely you can remove some moisture and reach to moderate drying, as you can see in this graph. In order to activate the smaller pores, what you have to do is that to increase the frequency, as you can see here. As you increase the frequency, you are increasing the driving force. Definitely you can activate most of the pores inside of the fabric and reach to even lower final remaining moisture content. The same goes on and on. As you increase the frequency, you can achieve better and better drying, but you have to pay for it. Here on the left graph, you see that as you increase the frequency, the energy consumption of the piezoelectric transducers, or energy consumption of moisture removal, is going up. So there is a sweet spot at which we can achieve both good drying and good efficiency at the same time. And that's what exactly we did in this project. If you see these numbers, you can see that there are huge potential for improvement of the efficiency if we can design the system appropriately. So what we have developed in the first year of the project, actually we focused on 4 main research areas. One was identifying and evaluating the correct piezoelectric transducers for these drawing applications, and we down selected actually two specific transducers among 150 transducers that we studied. We identified and evaluated the correct power signal. We realized that the amplifier has a big role on the efficiency, on the final efficiency of the system. So we actually customize the design of the amplifier and come up with one of the best designs. We also work on modulating or designing and modulating transducers so that we can modulate or scale up the system easier later on. And also we worked on developing the mist collection mechanism. So at the end of the year one, this was the prototype that we had, which could dry 14 square inch of the fabric. As you can see, the motor could easily remove from